Okay, so for problem CLISI 11, so we're computing flux. That means it's either Stokes' theorem or Gauss's theorem. Stokes' theorem wouldn't seem like a natural candidate here. There is no boundary curve, although technically you can talk about a flux through nothing, and it's just there wouldn't be anything. But Stokes' theorem would only apply if we could find an anti-curl. Now, for one thing, we don't know how to do that. For another thing, if it did have an anti-curl, that would mean the divergence was 0, which would make it a fantastic Gauss's theorem problem, right? And in fact, we already know that the surface is a boundary. So, in fact, so if Stokes' theorem applies at all, this problem is a trivial Gauss problem. So I'm going to say let's do Gauss's theorem. So certainly then the very first thing we're going to do, and that's really always the case, is we're going to take our vector field and we're going to do what the diagram tells you to do given where you are. We're computing flux. So the diagram says compute divergence. And the divergence here is, let's see here, well, that's 0 plus 0 plus 0, which is 0, right? So therefore, the flux through the boundary of this solid, however weird and ugly this solid may look, that flux, according to Gauss's divergence theorem, is triple integral of divergence, which is 0. Yeah. And here's another, by the way, just a strategic tip-off, and this is not mathematically valid, okay, but just, I mean, strategy. I hope you know that I am not a vicious person, right? And look at how ugly this problem would be. I mean, we've got the union of 3 balls that overlap. And I mean, doing a triple integral over something like that would be just brutal, and it would be not a likely expectation. This is from a strategic point of view that's going to be necessary, right? Does that make sense?
Yeah, yeah.
Okay. Anybody else? Everybody happy with this one? Okay. All righty. Let me stop the recording.